Thanks, man. Hope you guys can see my screen.
Yes.
Can you guys hear me?
Yeah, loud and clear.
Oh, yeah. Hey, thanks for your time today. Look, I'm Angelo. And before I move on to the content, I'd like to acknowledge and thank Alif, who's our technology architect, and Sophie, who's our marketing head, and Kevin, who's our business head, for borrowing the slides for me to let's steal the slides. Thank you. So yeah, look, I think a quick overview. We will go through what is Sync Machines about. What do we do? What does an in-cabin monitoring mean? How do we see it in the market as a leading DMS OMS provider, driver monitoring system, DMS and OMS is occupant monitoring system. And we will discuss about some of the challenges we face because I'm part of the embedding. I head up the embedding part of the organization. And we will talk about some of the trends and the solutions that we bring forward. And I'll conclude with some numbers of our custom, ASIC chip. So yeah, we are in Canberra. This is a co-pilot view. So we on the eastern part of Canberra. That's where our head office is. Yeah, and it's a spin-off from a university 20 years ago. So look, our mission, as you guys know, the fatalities are increasing, primarily also because of the rapid advancement of automotive based autonomous driving and the perceived misunderstanding of what the cars can do, right? So our mission is actually we wanted to reduce the fatalities or make it zero if it's possible. And we also want to make sure, we get the drivers back home. I'll go through some of the use cases that we have. So it's 20 years of scientific research. We are one of the leaders. We are basing off our tech based on human factors. How the human behave, how to interact with human. And obviously, we are a global company with people in engineering in Australia, United States, Japan, and other parts of the world. Very quickly, we got, I would say, 3 business units, but automotive and aviation falls under the same OEM business umbrella. So we do have a product called 4-Wheel Driver Monitoring Technology Platform, which I will go through what it is, what are the fundamental blocks of that. And obviously, we are considered the leader in the market. And we do have, multiple OEM programs, which I'll go through very quickly with you guys. And the most exciting part, recently, we got ourselves into aviation, working with Collins Aerospace, who's the leading tier 1 in the aerospace market, looking at pilots, co-pilots, understand the cabin. I'll go through some of the exciting use cases that we're working on. To the right, you see the aftermarket, that's where we retrofit stuff to the trucks, trains, rail, and all the other high-end vehicles where there are safety issues to monitor the person who's driving the vehicle. Yeah, and we also have an exclusive, I think it's exclusive, yeah. They are a global partner with Caterpillar, who's the mining company. Yeah, look, I think this slide is so exciting for me. The range of problems as a company, as an engineering team, we work on, starting from fleet. As I mentioned, it's a retrofitting a DMS system, wired up in the vehicle, power it, and then point to the driver and try to figure out are they distracted, drowsy, are they paying attention, et cetera, et cetera. And automotive, as you know, cars, it's going to be the cars today on my presentation, so I'll leave it for that. The aviation is a very exciting and interesting one, which just before we had interactions with Collins Aerospace, I simplistically, I thought, you take stuff that's pointing in the car, just, move it to aviation. But it turns out the challenges are completely different where, there's a pilot, there's a co-pilot, they can move around versus in cars, as you sit in the seat, you don't have a very crazy, abnormal posture, whereas in aviation, an abnormal posture is common. Pilots are allowed to sleep, So it's a very different cabin environment that you need to monitor for. It's a completely different, challenges. And obviously, as I mentioned, mining and rail, it's a similar challenge, but however, there's a lot of human factors research involved in terms of HMIs, triggering warnings and alarms and those kind of stuff. There are a few facts. I'm sure you guys know distracted driving. This is one of the biggest contributor of deaths these days on the road. There are some other statistics I'm sure you guys are well aware. So, I think just to set the scene, how much expertise we got in the company and in the group. So, it founded in 2000. However, if I want to quickly go through, so we had a OEM win with GM. That's probably the first start of an automotive in-cars technology development for us. And then we had a big milestone, the Super Cruise. Not sure you guys have heard. Cadillac is too expensive for me to even get into one of them, but however, we got our system there. So lucky enough that's still one of the leading car in terms of driver and driver monitoring systems, I would say. Then we got a lot of wins. We are also into full flight simulator. As you know, the aviation industry is struggling for not hiring enough pilots. So pilot training is very important for them. So we are providing technologies into the full flight simulators so that they can always monitor the pilots are following the right things at the right places and following the procedure, especially when there's emergency. We got a lot of other OEM wins. However, the Qualcomm partnership is another exciting one that we do work closely with Qualcomm and their new chips. They are probably one of the market leaders, including other chip manufacturers like TI, Umbrella. Again, also with OmniVision, we do have the Ocular, which is what I'm going to show you today, probably slightly deeper. And then the story goes. We also got, as you see, the Ocular is one of our, the custom chip that we made an ASIC out of. Yeah, that's the history. So we, look, I think as I previously mentioned, human factors is the fundamental building block for us, where we do our R&D on what the human, behavior is, how the humans interact, where they look, how the properties of the body is, and all that human factors. And then we build on top of that the three pillars, we call it, which are kind of a co-designed washing machine, I call it, where you don't see them as separate elements, but you see them as critical three elements working together to bring a system at the top, right? Because we time and time again we hear from OEMs and car manufacturers and tier ones. Sometimes the optical path is provided by someone, the embedded processing solution is provided by someone, the algorithm sits on top. If the three are not working together, you're always going to have a suboptimal solution. So we strongly believe in a systems approach. So we do all our feature development ground up, considering all these three pillars in parallel. Regulatory roadmap. I'm not sure whether you guys are across it, but obviously this is definitely increasing momentum in the recent time, starting with 2022, China GBT at the bottom here for phone, smoke and eyes closed and abnormal head posture. That was mandated and together with the European Commission's drowsiness and visual distraction. And then from that point onwards, now the politicians and the lawmakers are now looking at ways to bring safety into roads, right? And even my boss Mike Linné, who's the chief scientific science and innovation officer, he was at US last week discussing about NHTSA. We are part of NHTSA. We work with NHTSA. We are part of the Euro NCAP committee. So we actively work towards, supporting and guiding these regulations. But to the right, just to give you guys an idea where the regulation is heading, is where they wanted to do. That's an excerpt from the Euro NCAP 2030, plan. So the three things they called out was, crash avoidance, crash protection, and post-crash safety. So that's going to be, the three segments that every in-cabin monitoring provider has to address, right? You avoid the crash, You find ways to protect the crash, or signal the occupants and the driver. And then if crash happens, how do you quickly react to call an emergency ambulance and those sort of stuff. Well, look, if you guys have heard a lot of news in LinkedIn, there's a lot of promises. However, the autonomous vehicle projects are not doing well, right? There's a lot of history on, Apple shutting down recently, Argo AI, they were shutting down, who shuts down, all the other, even, premium car vendors are scaling down on those projects because they're realizing the driver has to be in the car. And there has to be a camera-based driver and in-cabin monitoring for a long time until we get the infrastructure and all the other stuff in place. Well, as a side note, we do provide a system or a solution, a product called Backup Driver Monitoring System, where we monitor we call it backup driver because, this is an autonomous vehicle or car. You sit as an evaluator, you try to assess what's happening to the car, right? So we do monitor that person and provide them logs, monitor their the way they can record videos and all that. So that's one of the product lines we sell, and it appears to be well sought after these days because of these, the projects trying to understand what's happening. Look, the two different software stacks, I would call it, which will combine together with where you place these systems in the car, especially cameras, right? So when we say standalone, it's where you have a ECU or an SoC, which is dedicated for in-cabin monitoring, driver monitoring or occupant monitoring. Versus integrated means you have multiple applications combined together, sitting on a chip. I'll discuss some of the challenges in the future slides, but where you have DMS, OMS, contained inside an application where it has, with multiple cameras is running, or, radar, LiDAR, some of that, other applications where the cameras are looking out, or other, entertainment algorithms, graphics and all that. So at least from our point of view, these are the most, popular places where the car manufacturers are looking into putting cameras and the systems. Obviously the steering wheel column is one good example. I'm sure you guys have seen enough videos if you're into these in-cabin monitoring technologies. A-pillar, on the side of the car, next to the windshield. That's another position where they're trying to host a standalone box. You hook it, push it to CAN, and off you go. Versus an instrument cluster, it's a very powerful chips. They're housing instrument cluster primarily because the graphics and all the new techniques. So we can actually integrate stuff in there. The biggest one which we are excited about is the standalone on the mirror, right? Because I'll show you a couple of demos to excite you guys, but that's the new latest toy, I would call it. The other one is headliner, as you know, above the mirror on the line, to see as many people as you can. And then obviously infotainment, as you know, there's a lot of chips being considered, a lot of demand for infotainment, the software-defined radios and all the complexity of software, and the chip manufacturers are providing support to increase the power or the capacity or the processing power, and then we can house the DMS in there if it's possible. Then obviously that's central ADAS compute ECUs that are very popular, trying to bring these 30 chips into fewer and fewer chips, so the car manufacturers can centralize the processing in fewer nodes or fewer SoCs and try to cut the cost. So these are the few of the places we do know that there are things like B pillar, which is the the sidebar, and there's also overhead locations at the back. So the OEMs are thinking various ways to map them. So this is probably one of the recent toys that we are playing with. It's a cool mirror. If you look at to the left, that is designed by Magna, who are our co-partner. It's a very sleek mirror. You can't see the camera inside nor the lights. It's super cool. You still hold it, you feel like mirror, and there's no you cannot tell there's a camera in there. And to your right is what the field of view you will see of the cabin. I'll show you a demo very quickly so you'll understand how I think that the imagination or the Knight Riders. I don't know if you're old enough like me, you will know what Knight Rider series is, but it's getting to the point where the car will understand a lot of the stuff about you and the occupants. So I'll quickly run through this. Hopefully this will excite you guys to see what a car see these days, right? This is close to the mirror. You see there are 4 passengers coming in. So it's detecting the left passenger, right passenger. And at the top, you see they're saying, okay, they occupy the seats. The 4 passengers occupy the seats. It's going to identify the driver and the passenger. So it says one is Majid and his age and his gender, and Andrew and his age and gender. And it also checks whether have you got the seat belts on, these icons here. Those are the seat belts icons at the top. And it's going to now look at, are you looking, are you distracted? Are you sleepy? And also if you look at it, it's also tracking your body. So it already knows you're holding something in your hand or you're wearing mask. And this is a very good one. So it's detected it's holding a phone, the passenger is holding a phone or the driver. So it already knows, and he's speaking. So he's going to hand it over to the driver. And it's going to also detect the driver is handling the phone. And in the meantime, you also see, so now the phone is getting detected on the driver's side. And in the meantime, it's also checking whether the driver is, attentive. If you look at it, it's checking, is he looking on road, is he looking off road, and those sort of stuff. And expression, you see that, it says, is he smiling? Is he laughing? Is he yawning? So that's those. So if you look at it, how a car can understand with just a camera in the rearview mirror, just in a very small chip, very tiny chip, right? It's amazing how much the technology has improved and how much a car, the system can understand the properties of each of these 4 passengers. And if you look at that now, it'll also finding it's saying he's laughing for a joke. I'm not sure he's going to take up a smoke, but so this is I'm hoping you can appreciate how much features go into these chips to satisfy. Okay, it's going to say he's smoking. So it knows, that there's a smoker in the cabin. And obviously there's also a China GBT, which dictates that we need to detect the smoke usage, right? I don't know whether you guys have any questions, but just to give you a sample of what the cars these days would understand about the in-cabin. And there's much more. I'll run through some of the other examples that I can talk through. I think yawning is a classic one. As you know, you definitely want to know whether the person is yawning because, that's a sign of fatigue. So it's a very important feature. Probably I can move on. I'm sure there are more videos, but look, our scale is milliseconds. Not sure that means anything to you guys, but for us, being in Canberra, the travel is hours. I'm sure if you're in Europe, it's half an hour. You go to a next country, but for us, the next neighboring state is 6 hours, right? So the driving is part of our life, and because it's a long drive, there's a lot of events happen towards getting into a fatigue accident, for example, right? However, when something happens, it's always a millisecond reaction time, right? For example, if the driver is sleeping, and then they're just about to doze off, and then within milliseconds, we should be able to figure out, okay, what do we do, right? So our time scale is always milliseconds. And if you know the camera technology, the driver monitoring camera technology used to be like 60 hertz, 54 hertz, which is like 16 milliseconds window every frame. Now it's gone to 30 because of this RGB wide field of view camera. So that's every 33 milliseconds you're going to get a frame, right? So you should be fast enough to whatever features you saw in the previous video, you should be able to process all of that within the 33.33 milliseconds, right? So it's an exciting challenge. How do we optimize all these applications into that 33 millisecond budget, so we're able to prevent an event like this, which is within a millisecond reaction time, right? So as the regulation mandates more of this, pre-crash impact and post-crash, we see a lot of features being asked for understanding where the person is, what's their height, where are they located, how big they are, how small they are, and things like that, so that there are things the car can do pre-crash, so that it can have a lesser, significant impact, and having some, mitigation plans after post-crash. What do you do, right? Who do you call? If it's an old person, you want to call, emergency straight away, things like that, right? So car is going to rule all these decisions with these kind of technologies. So just I took this off this paper from Mishra, I think. So look, I think this hopefully will give you what other stuff the car. So now you saw what we can do now, today, in the previous video. But if you take that and look into a bigger context, because hopefully you have seen the field of view that you see all passengers, right? So if let's say if we can fit 6 seats or 7 seaters, even you will be able to see all 7 of them, right? Because the camera angle is very high. So now the good and the exciting thing for us is to figure out, okay, what's next? How do we understand these different contexts? Is the driver on a rage, trying to attack the passenger? In the middle, number 2, you'll see a family. Are they singing? Are they really angry? Is it chaotic? Should the car stop? Is the husband going crazy? Or they're just generally singing, right? So that context is important. Probably a love moment. And the number 4 is more, casual. Should we display, stuff on the side mirror? Are they looking for a good vibe? Lights, music. So if they know that context, they can play. The car can play and set up the mood, right? And the 5th one is very important. Smoke and smoke phone, as you saw previously, and also how that affects the rest of the cabin. The other thing you haven't seen, unfortunately, I didn't get any pictures. I should have. It's the car seat. There's a lot of interest in car manufacturers about leaving child behind, or leaving your pet behind. And these kind of technologies, understanding what's happening in the car, will help us figure out what to do, right? Probably car can give the driver a call, saying, okay, you left your dog, but you forgot to pull the mirror down, right? For example. So it's amazing what what applications we can apply, knowing that we already have that tech that I showed you before. With our Ocular, ASIC chip in it, which we designed together with Omnivision. And obviously the SoC is there. We will have an accelerator, which is sitting in. I'll show you some block diagrams how it's plugged in with the SoC. The sensor is very important for us. The lens, as you saw, is it a narrow field of view, only looking at the driver, or is it wide field of view, looking from the rear view mirror, looking the entire cabin? And the LEDs, it's infrared. So we have 2 different categories or more, depending on who you talk to. For us, the primary difference is, you have LED, which we call it dark pupil, where you have the camera or the sensor, and the LED is slightly away. This configuration here that you see in the picture, versus we call it bright pupil when the LED sits next to the sensor, right? So these are the 2 primary differences. And obviously, you have a serializer sending images into a deserializer and then back into the SoC. On top of that, as I mentioned, the brightness is a very important aspect of a good DMS or in-cabin monitoring, where for example, a brightness control of you facing sunlight straight will be different to you facing the other way with a lot of shadows, right? So you need to have an effective closed loop optical path with a good, LED control, which is why we work with a lot of LED drivers, with a lot of partners with Maxim TI and all those guys to find the best, optical illumination possible in the cabin provided. So these are the standard OMS or DMS parts that you will find in any product line. So the biggest challenge we have, there's so many features as you just heard. It's limitless. Car companies are looking for many things. What you're wearing, what color dress you're wearing, what is your mood about, are you fat, are you pregnant, on all those kind of properties, even so that the tech can understand how to drive you home safe and also react to certain incidents. Then on the other side, if you see the complexity in the cars, amazingly, it's going through the roof, right? So many sensors, so many new techniques, and so many parts, all going software, electronics. It's the number of interactions a car needs to have is very complex. And the third one is the SoC, where obviously our software, we are a software house primarily. We have to sit on top of an SoC, which is provided by we got partnership with Qualcomm. Obviously, we work with many other SoC providers like TI, Umbrella, Omnivision, so and so, right? So SoC vendors also building up their tech very fast. Today you'll see a Qualcomm chip with an NPU, and they will in 2 years they'll come up with a different NPU with a different architecture. They'll also have different memory architecture. Once they'll have different NPUs talking to each other, the other NPUs will go to DDR and come back. It's amazing. And then on top of that, you also have operating system vendors, right, driving these chips. So now, even in Qualcomm family, we got QNX, they got Green Hills, different operating systems, and they obviously Linux is one, but it's not real time. And then you got the container-based or GVM-based. Qualcomm has, I think it's called multi-GVM. It's a container-based which will run Android, Linux, and QNX. It's amazing, right? And running a software on top of that, it's excitingly challenging. How do you optimize your software to work with those kind of setups? And on the fourth one, as our principal scientist Akshay Astana would say, every day he'll come up with new networks, right? So it's very interesting how the neural network market evolves. Yesterday will be mobile net or something, and then today it'll be transformers. Tomorrow it'll be something else. It just keeps changing every day, and based on the different technologies, we now have to figure out, okay, how do we move to this network, because that's more accurate, faster, smaller, efficient, right? So it's a very exciting place to be at least for us as an embedding group. Then we get to figure out, okay, how do we design a solution which can last for 3 years? Because obviously an OEM car software delivery program will be around 2 to 3 years, right? So basically you start planning 3 years before, but having to figure out all these varying degree of complexities. How do you design, right? So that's the challenge we have. So moving a bit slightly further, obviously one level down of this complexity, signal accuracy is the biggest part of the game, right? So you want to be as much accuracy as you can, so that you can prevent all the things that I discussed before in millisecond granularity, right? But however, that comes with a cost, right? Because using 64-bit full floats versus quantized 8 bits, you're saving that much of bits, but then you're trying to reduce the accuracy, right? So that's one degree. The next one we care about is actually the CPU load, because the CPU is a precious resource, primarily because a lot of vendors want to click compile and put it in their CPU, right? Because there's the design is less complicated, integration is easier, at least perceived easier. And then, so basically like a tier 2, like us, a provider who has to sit in in multiple of these software stacks, CPU load is a challenge for us, and we try to optimize our software to reduce the CPU load. And then DDR bandwidth, I'm not sure how many of you guys know. Recently, a lot of the chip manufacturers are coming up with the quality of service for DDR controllers, where you get priority for a certain amount of time, then a different master will get a priority. So there's a lot of bandwidth issues or challenges going on. And also, as you know, the more and more high resolution cameras we get, obviously we had to push a lot of data into the memory, right? And that's going to affect the DDR bandwidth. And then obviously ROM and RAM usage, because that costs money, because going from 250 disks to 512 will cost you dollars, right? And then you sell a million units, then of course it's going to cost you $1 million. So how do you have lesser footprint? Because as I mentioned, you're driving for an hour and then you hit the millisecond mark to get to the event. But how do you utilize the memory and not just store everything, because you can't, and then find a way to create a history and then react. Accelerator research is one of the biggest strength we have in the company. We have when we say accelerator, using DSP or NPU or GPU or any other accelerator other than the CPU available to run your software. So we have done many of these custom acceleration because we wanted to reduce the CPU load, and we got a good capability to do that efficiently. But the issue is accelerator also cost power, then of course it's heat. And the other one is cost, right? The car manufacturers and tier ones and us, you always have to worry about cost to get the money back, right? So you can't have a, I don't know, like $100, $200 chip to squeeze everything in. You want to bring that down as cheaper as you can, but still being able to implement all the features that you want. The other interesting one, which is very exciting for us, it's boot time, because there's a lot of vendors want to start the car and the features as soon as we can. As soon as you open the door, they wanted to greet you. The car wanted to say to your profile, arrange the seats, make sure it invites you, put your song, all these amazing features. They wanted to get that up into the CAN bus, into the car as soon as possible, right? So this is an exciting challenge for us to figure out, because as you know, a booting process, a power on reset will involve, starting from the drivers to OS to, even if it's FPGA, even powering up PL to PS to all the way the stack, right? And then we sit right at the top as an application. So that's definitely one of the very good challenges for us, and we have delivered in many such constraints. Probably the last one, I would say, the heat and power. As you know, the rear view mirror is a very good example, right? Because the cars get hot really high, especially in summertime. I don't know about where you guys are, but in Australia we do get 30, 35, 40 degrees hot sun. It gets really hot, especially in the front side of the car. So it's very important you design your software which can run on chips which has a lower power, heat, and footprint. But then obviously for the static and dynamic power, they need to run smaller, efficient hardware. So yeah, look, I think this is exciting challenge. That's why I had the diamond there, because by the time we come out of a solution considering this, we would have solved many exciting engineering problems. So, to cater the industry, we have 3 different software stacks. 4VO chip. I'll quickly run through what it is, but it's an end-to-end for the standalone parts I was mentioning. So basically, we own everything from the OS to the hardware to the So Xilinx owns the hardware, but we provide the PL bit streams and FPGA based ZTU. Then we provide the drivers, Linux, and then all the way to the software stack. And so basically it's plug and play. The customer buys it, put it somewhere in a car where there's free space, hook it up the CAN, off you go, and put the camera. So that's an 4VO chip program, which is in production already. So to your right, you see the EDME. It's an API-based, classic software integration software that every tier 2 business provides. You give an API-based application, and whoever wants to integrate can hook up your application with their system application, and then they build up the system. The third one is, as I mentioned, we do have our own ASIC and our own, Ocular, which is specially designed for in-cabin monitoring. So what's in, 4V chip at a high level? You like every other chip, you'll have a DDR3 module or DDR module. You have a flash storage to persist the data for every restart. It could be a NOR or an AND. We got a lot of, various communication interfaces. And obviously to your right, that's a camera, right? I'll quickly go through the next one. So this is one level down. If you are into cameras, you'll know, the SerDes. So the SoC talks to the serial assay, deserial assay, which is SerDes, to the image sensor. And there's a back channel coming back where you need to know when the camera goes on, or the flash opens. So, yeah, flash opens, or flash, which opens the sensor. And then you pull that back and you align the LED so that they align, right? So that's why the strobe signal is coming back. The IR illumination, there are many ways we design the LED driver, as I previously mentioned. And this one has an I2C into the LED driver so that you can tune the pulse so that, when it's too bright, you want to go dark. When it's dark, you want to go bright. Yeah, there's a NAND flash and a DDR. And the safety microcontroller, you have it at the right side. It's more as it creates a safety island, right? So basically you can switch off, power off, pick up errors and report back to the CAN interface. So this is an overall 4V chip that we have, and every product line you see in the same cabin will look very similar, the component wise. One important thing to mention here, this is a template architecture. As you know, we work with many ARM CPUs, and we got a lot of custom neon instructions to parallelize and efficiently execute stuff for CPU systems. So the difference between a standalone versus integrated will come in play if you understand this architecture, where you got local caches, you got a shared cache between a CPU subsystem, you got a system interconnect, and then you got an NPU and ISP, right? So based on how you use the data and process the data will affect what sort of performance you get, especially when someone else is sitting in your CPU subsystem, right? So for example, if our DMS is sitting with a ADAS application, obviously there's going to be some cache thrashing at L2, and then obviously that'll end up letting our application have to go to more DDR. That's going to potentially slow us down, right? So those are the challenges we come across and try to optimize our software, especially when there is an integrated software stack. Yeah, this is another example how our Ocular, as I mentioned, our accelerator sits. It's another classic architecture where we sit on the system interconnect together with all the peripherals, and then it acts as a core processor. You put in an RPC, send the DMA things across, it'll execute and give that interrupt back, and then you run with the results. So just quickly run through some numbers for you. I'm hoping probably you want to know what are the magnitudes are compared to an integrated versus standalone. So our 4V chip, as I mentioned, standalone unit. Since we have, it's probably not a surprise, since we have customized our Ocular accelerator to support in cabin, ours perform close to some of the most efficient ones, and obviously the integrated one has a high demand because it's supposed to execute an ADAS application on top, right? Yeah, so this is another RGB-IR use case. I'm not sure how many of you are aware. So RGB-IR sensors are getting really popular. So this pipeline is getting very, very popular in the automotive industry, especially when the car manufacturer also wants to have zoom effects, color. While you process the IR, they also want color rendering on the display and all that. So some fancy stuff. So this pipeline is very popular. And obviously, if you want your application to execute efficiently, you only want to go back to DDR once, right? So I mean, it's by design. You need to do that, because some SoCs, you take a image, go to DDR, come back, do the downscale, go back and go to the DBA. It's by design, right? Versus for us, because we had the liberty of creating custom accelerator, so we managed to have put in some tricks in the ISP so that we can do everything in flight, right? So we process everything, so we only go once to DDR. So that's why we are quite efficient. Again, I don't want to go through in detail here, but just a high level. Again, the same pipeline, but what you see here is because we do everything in the ISP itself, our video input bandwidth is very low. However, our compression is not so good because we don't have high sophisticated compression techniques like other SoC vendors. However, this we will tell you, we still, even though our chip is probably less powerful compared to other SoCs, few of the SoCs compared here, we still got a lot of room to play with, primarily because we have a very good ISP design, right? So we don't have to go back to DDR every time. Yeah, again, this is just a reference network, because this is off the open, because we do have custom networks, so we don't really use these networks, but these are just examples. But hopefully it's very obvious and intuitive, where the faster the rate that you want to run the networks off, you will have to cost for more memory access, right? So assuming no caching, right? So that's what you see. So basically, it's even the biggest network here. It goes probably 4 times if you want to run at 30 hertz, which is the standard sensor rate. Again, another view, but at a higher level, the pattern seems to be in most of the applications where you have smaller networks, running slower, versus medium networks running slightly faster. And it seems like, the 1 or 2 big networks running every frame, right? As I said, the typical frame rate of sensors these days is 30 hertz. So latency differences, as latency, as I mentioned, our scale is milliseconds, right? So we always want to react in milliseconds time scale. And for a chip, which is our chip, because obviously, as I said, we design in such a way it will be very efficient for in-cabin monitoring. It can run 3 milliseconds versus some of the slow ones are 57, even though the TOPS is higher, right? So we built in an efficiency in there deliberately. This shows you the capacity of how much capacity we have in the chip, because as I just mentioned, it's also depending on how much bandwidth you use and the latency you consume and how much efficiency you have. So our chip definitely have more capacity, as you could see, compared to others, primarily because it's heavily custom designed with our accelerator. Again, a similar view. I'm not sure what you can get out of this other than just to say, if you look at our ASIC versus Ocular and all the other TPUs in the market, high-end TPUs, obviously ours is much efficient by design. This is a good overview for anyone to understand what are the proportionate of if you take a general SoC, what is the proportionate of CPU versus vision accelerator versus ISP versus other peripherals versus memory, right? So the important factor we usually show you to customers, CPU is 20% and your vision accelerator is 15, right? So where do you want to map your software for maximum efficiency, knowing that CPU is the one which is well in demand in most of the cases, right? From an integration point of view. So yes, this is an example where if you think the one A53 is a relative efficiency, it has an efficiency of 1 in terms of the area versus latency. Our analysis says, we are 12 times better, primarily because, our Ocular is designed together with the ISP in a way that it can efficiently execute the DMS and OMS application. Yeah, I think that's it from me. Hopefully, you guys learned something new. And not bored you with too much information.
Thank you, Jude. Thanks a lot for the lovely presentation. The floor is open for questions.